Okay, so we're going to start our final exam review today, focusing on kinematics. Okay, go over some of the key concepts, and then I'll take questions from you guys, and we can go over whatever it is you need us to go over. Okay, but firstly, do I have all the assignments that are coming in today? Doesn't seem like that pile's quite thick enough. All right. So first thing that we went over in kinematics was we reviewed scalars and vectors. Okay, and we're not going to spend a lot of time talking about that now because we don't need to. Okay, you just need to remember what quantities are scalar, what quantities are vector, because on a final exam question, if it says here's a bunch of stuff, calculate the final velocity, you want to make sure you're calculating final velocity and not final speed, because obviously you calculate those differently, and you don't want to make a mistake like that. Okay, so really that's what you need to know about the scalar versus vector quantities. Nothing really new. Okay, we talked quite a bit about graphing in Unit 1 as well, okay, especially velocity versus time graphs and position versus time graphs. Okay, expect that you're going to see some graphs on your final exam. Okay, sometimes in the multiple choice where it's just interpreting a graph, but also expect in the written response section that you're going to have to do some graphing analysis. Okay, and what I mean by graphing analysis is if I give you, let's say, a position versus time graph that looks like this, and I give you the equation for it, that you'd be able to calculate some things for me from that position versus time graph. Okay, some of the things that we can calculate from a position versus time graph are velocity. We can calculate speed. We can calculate displacement. We can calculate total distance traveled. Okay, all of that kind of stuff. So we got to remember how it is we do that. Okay, if it's a linear graph like this, we've got to remember how to use y equals mx plus b. Okay, remembering that m, in this case 0.576, is the velocity of the object on this graph. Okay, that 2.5 is the initial position of the object and things like that. Right? If you were given a graph like this, but it wasn't linear, okay, and it was jagged or went all over the place, then you'd have to remember, okay, if I want to calculate displacement, it's final position minus initial position. If I want to calculate the total distance, I've got to add all the sections together. Okay. Finding average velocity on a graph that's not linear, okay, then I've got to find my total displacement divided by my total time. Okay, for speed, total distance divided by total time. Nothing you haven't done lots and lots of times before. It's just been a while since you did it. Okay, so make sure you have a look at like the worksheet booklet, okay, that's on Google Classroom, because there's a bunch of graphs on there where we did a lot of that stuff. Okay, so I would have a look at those, make sure that you can still do that kind of graphical analysis, that you can still use y equals mx plus b, because that kind of stuff is definitely going to be on your final exam. All right, after that we talked about acceleration. Okay, acceleration is important, not because there's going to be a ton of marks on just like an acceleration problem, because we're kind of past that, but acceleration is part of a lot of other things. It's part of projectile motion, okay, being able to use the formulas and know which one to use. It's part of Newton's second law stuff. You have to figure out what the acceleration is to calculate m times a and things like that. So being able to identify what acceleration formula to use and use them is certainly important. Also knowing what acceleration is important. Okay, yes, an object is accelerating as long as its velocity is changing. Right? And in this unit, that was really the extent to which we needed to understand it. Obviously, we understood it a little differently, in Unit 2, where we had to start talking about the forces that caused it and things like that. But for this, obviously be able to use formulas. That's supposed to be a U. Looks like a W. Okay, yeah, so just make sure that you can still do that stuff and understand what acceleration is. Okay, calculate it from a velocity versus time graph, those kinds of things. All right, then the thing that we spent probably the most time on in this unit, vector component addition. You are definitely going to have to be able to do that on the final exam. It is a crucial skill for you to possess coming out of Physics 20, because when you get to Physics 30, the very first unit is about momentum. Okay, and momentum is all vector stuff. So being able to draw those vector diagrams, tail to head, calculate X and Y components, and all that stuff is going to be crucial for you. So let's quickly review how that works. I'll just put an example up here and then we'll walk through it. Okay, so okay, so this will be, you know, a relatively straightforward one here, but they're both angled, okay? We don't have any perpendicular ones or anything here. All right, so once we have the vectors, the first thing we want to do is draw them both tail to head. So we've got 200 meters at 30 degrees north of east. So I want to draw a reference line that is east, okay, like so, and I'm going to go 30 degrees north of that. Okay, this line is 200 meters long. This angle is 30 degrees. This is the X component, and this is the Y component of that vector. Is that ringing a bell? Then I draw the next vector on the head of the first one, unless I'm using the separate triangle method, and then we're drawing them separately, obviously. But okay, so I'm going to again draw a reference line that is due east because my vector is measured from east. Okay, and we're only going 10 degrees south of east this time for 150 meters. All right, so here's our Y component, here's our X component. Okay, this is 150 meters. Okay, this is our 30-degree angle here. Okay, now we have our two vectors. Yes. Sorry, it should be 10. Sorry, you're right. Oh, I messed up my whole diagram. Sorry, 10 degrees. Okay, and then I can draw my resultant. Okay, my resultant in this case is the total displacement of this object, and that always goes from beginning to end. Okay, and that's going to represent our total displacement. So that would be like your first mark, okay, for a question like this, is drawing the vector diagram for that question. Now, if I'm going to find out how big D is, okay, the blue triangle, then I have to know how far horizontally this thing goes and how far vertically it goes and in what direction. So I've got to find all the X's and all the Y's for the two vectors that make this up. Okay, so I'm going to have to find black X and black Y first, and then I'll find red X and red Y after that. So black X is right here. It is the adjacent side to the angle in that triangle, right? And I know the hypotenuse. So that means I'm going to use cosine of 30 degrees times 200 in order to get black X. And because Y is the opposite side, I will use the sine of 30 times 200 to get Y. That'll be 100 meters. So that one we can do. Okay. And then we'll have cos of 30 degrees, okay, times 200 meters. All right, so we got 173.205, we'll say. And obviously we want to keep all of our decimals. Okay, so this is east, and this one is north, right? Always important to keep those directions on there as well while we're doing this. Now I need to do the same thing for the red triangle. Okay, so I'll have red X and red Y. Okay, for this one, X is again the adjacent side. So I'll have the cos of 10 degrees times 150. And for Y, I'll have the sine of 10 degrees times 150. All right, so we got 147.721 meters, and that is east. And then for y, we'll have 26.047 meters, and that is south. Okay, what do I do next? Well, one of them I'll be subtracting, and one of them I'll be adding, okay? Right, okay, because black y is north and red y is south, okay, I have to subtract them in order to get blue y, okay? Blue y is obviously the difference between black y and red y, okay, because I went north and then came back south, right? But blue x is the sum of black x and red x, okay, because they're both going the same direction. So that's my next step, is I need to calculate my resultants x and my resultants y components. All right, so blue x will be our 173.205 plus our 147.721. Okay, and I'm rounding off here, guys. Don't do that. Obviously, I'm setting a very bad example here, but okay, just for the sake of speed, 320.926 meters, and that one is east. Okay, then blue y. Okay, blue y we calculate. We said we were going to subtract because those vectors were opposite. So we'll have 100 minus 26.047. And that's going to be 73.953 meters, and that is going to end up being north. Okay, the line on my triangle clearly showed I still ended up going north overall. Okay, now that I have those, what can I calculate with those? Yeah, I can calculate D. I can calculate the resultants magnitude, and then I'll use them to calculate the resultants vector as well. So first thing I need to do is do a Pythagorean theorem calculation. All right, so my overall displacement, which is my resultant, okay, will be 320.926 squared plus 73.953 squared. Okay, so 329.337. Meters, okay, is my total displacement, okay, from start to end. And then I also need to calculate my vector. Right, to do that, I'm going to use y as the opposite side and x as the adjacent side. So theta will be 10 to the minus 1 of 73.953 divided by 320.976. All right, so we're looking at 12.975 degrees. And which way is that, according to my diagram? North of east, exactly. All right, for significant digits, and that's not something we want to forget about either, I only have 2 because the 30 and the 10 are only measured to 2 significant figures. All right, so our final answer here will be 3.3 times 10 to the 2 meters at 13 degrees north of east, or at 77 degrees east of north. All right, is that ringing a bell? Okay. I wouldn't expect the one on your final exam to be more difficult than that. Okay, in fact, it'd probably be easier than that one. Probably have one vertical or one horizontal line and one angled, just like your unit exam did. Okay. All right, also when we were talking about vector addition, we talked about a certain kind of vector addition question. We talked about boat questions, which were useful because they they helped us work on perpendicular vectors, but also because they gave us that two-dimensional nature of projectile motion as well to kind of look at. So if I've got a river that is 100 meters wide, and I can row at, let's say, 3 meters per second, so I can row like this. Okay, the stream flows from left to right across the screen here, and the current flows at 1.5 meters per second. Where do I draw that? Downstream and off the head of the first vector, okay? Because it's the combination of my rowing and the current that produces what's actually going to happen to the boat, right? If I had like a drone, flying over the river, okay, what the drone would see is the red line, right? But mathematically speaking, it's the green line and the blue line happening at the same time. I'm going across, but I'm also going downstream at the same time. All right, so the question might ask you, what's the resultant velocity of the boat? Okay, and if it did that, then you would find the magnitude of the red line and the angle. Now, again, the question may ask you, which way, or it may say like from the shore. If it asks you from the shore, then it's that angle there. Right, and that was something that got a few of us on the unit exam, was forgetting that it specified which angle it wanted. All right, so it's not a difficult question to do. Okay, we just have to do Pythagorean theorem there. So, all right, so our resultant is 3.35 meters per second. Actually, it's just going to be 3.4 because we only have two significant figures. Okay, and then we would have the angle, okay, whatever that ends up being. Okay, so from shore it would be 63 degrees. Okay, now the next part of the question would probably say something like, how far downstream will you end up when you finally get across the river? Okay, so what do I need to find out before I can find out how far downstream I go? Right, I need to know how long it takes me to get across, because the whole time I'm rowing across, I'm also going downstream. So I don't have enough information to get the time from the horizontal part of this, from the downstream part of it, but I do know how wide the river is, and I do know how fast I'm crossing it. Right? It's 100 meters wide, it's 3 meters, or I'm traveling at 3 meters per second, so we're going to be looking at like 33.3 here, okay, as our time. Okay, so it's going to take me 33.3 seconds to get across the river rowing the way I'm rowing. Again, the whole time I'm going across the river, I'm also traveling downstream. So that means that if I take this number and multiply it by the current speed, I will know how far downstream I end up. 50 meters. Okay. Ringing a bell? All right, so those are the kind of vector addition things you could encounter on the final exam. Once we got done all the vector addition stuff, then we talked about projectile motion. Okay, and the reason we did projectile motion last is because it incorporated basically everything but graphing from the unit. We had to be able to do v equals d over t calculations. We had to be able to do acceleration problems. We had to find vector components and do all of that kind of stuff. All right, so I will tell you right now that the first problem on your final exam is a projectile motion problem. Okay, because it's a simple way for me to assess basically everything in the first unit in one question. So let's have a look at kind of a typical, or how a typical projectile motion question looked in this unit. Okay, so that would be a typical projected at an angle projectile motion problem. I'm going to give you a couple minutes to attack that one, see how far you get before I do the whole thing. Okay, so for projected at an angle projectile, okay, obviously it's going to follow a path that looks like an arc, and it's going to re-encounter the ground some horizontal distance away. This angle here is the angle that it was projected at, 40 degrees. This is the speed, or the velocity it was projected at, 15 meters per second at 40 degrees above the horizontal. Okay. For all projectile motion questions, we want to break them up into their vertical and horizontal parts, because the two parts are different. Vertically speaking, the object undergoes accelerated motion due to gravity. Horizontally, the object travels at a constant velocity. Okay, so we can't use, the only piece of information that can go across from one to the other is time. All right, so vertically speaking, here's what we know. Okay, we know that the acceleration due to gravity is negative 9.81 meters per second squared. Right, and that's it in terms of stuff we don't have to calculate. Stuff we can calculate is this. The initial triangle for this vector is that this side is the initial vertical velocity, and that this side is the constant horizontal velocity. Okay, they are the components of the projected velocity. Right, so can I find those? Right, I have the angle and I have the hypotenuse, so I can find those. So I'm going to find VI by going sine of 40 degrees times 15 meters per second. All right, so the initial vertical velocity is 9.64 meters per second. Okay, if this thing is going to go up and then all the way back down to the same height, what's VF? Nope. Same thing but negative. Okay, it's going all the way up and slowing down till it stops. Then it's going to fall the exact same distance at the exact same rate of acceleration. That means it's got to come back down going the same speed it left at. Okay, so VF will be negative 9.64 meters per second. All right, what can I find with those three things? Time. Yeah, and I'm always looking for time. In every projectile motion problem we ever did, time was the thing we were looking for because it could be used in both the vertical and the horizontal parts. So let's calculate time right now using this formula, VF minus VI over A. All right, so for us that's going to be negative 9.64 minus 9.64, okay, divided by negative 9.81. All right, so we're going to take that number there, and we're just going to multiply it by 2 because that'll work. Okay, and then we're going to divide it by 9.81. Okay, so our time here is going to be 1.966 seconds. All right, so that's what we've got there. Time I can take over to this side, 1.966 seconds. All right, the other thing I can calculate horizontally is the horizontal velocity. So I'm going to do that calculation next. So V horizontal is going to be the cos of 40 degrees, because it's the adjacent side, okay, times the 15 meters per second. All right, so we got 11.491. meters per second. Okay. Okay, so now that I have that and I have the time, can I calculate how far it will go horizontally? Okay. Since it's traveling at a constant speed, I can use V equals D over T. Okay, so D equals V times T. I take that number I just calculated, okay, and I multiply it by 1.965711343. Sorry, 345. All right, so it's going to travel 22.6 meters. Actually, I only have two significant figures, so it'll be 23 meters horizontally. The other thing that the question wanted us to calculate was the maximum height that the ball would reach. All right, so the maximum height occurs right here. How fast is the ball moving vertically at that point? 0. Okay? It is at the peak of its flight. It has been slowing down, slowing down, slowing down all the way to that point. So its velocity at that point is 0 meters per second. So now we have an additional piece of information. VF is 0 meters per second at this point. VI is still going to be the 9.64 that we calculated here. The acceleration is still going to be 9.81. Right now, we just have to calculate the vertical displacement at that point. That's what height is, a vertical displacement. So I'm looking for D. I have both velocities and I have the acceleration. So that means this formula here. Okay, that will get me D, okay, with the information that I have. So I'll have VF squared minus VI squared over 2A equals D, right? So that will be, it'll be 0 squared minus 9.64 squared divided by 2 times negative 9.81. Right? So essentially we have 9.64 squared divided by 19.62. All right, so the vertical height reached by the ball will be 4.7 meters. All right, so that would be, I would say, a final exam level projected at an angle projectile motion problem. Now, we did go over one other kind of projectile motion problem, and that's the ones that are projected straight out, horizontally. Okay, so that would be like something drives off a cliff. Can I go to another slide? Anyone still need this? Okay, so something goes off this cliff at 20 meters per second, hits the ground below 25 meters away from the base of the cliff. I want to know how tall is the cliff. Okay, so as we said, the first thing we want to do is break this up, as we do with all projectile motion problems, into the two components, horizontal and vertical. Okay, horizontally speaking, we know the distance traveled is 25 meters, okay, and we know the speed horizontally is 20 meters per second. So if we want to find time, T will equal D over V, which will be 25, okay, over 20. All right, so that's going to give us our 1.25 seconds. All right, that I can bring over to the vertical part. Time equals 1.25 seconds, and the acceleration is 9.81 meters per second squared. I don't have to make that negative in this one because it's not changing directions. It's falling down the entire time. What's the other key piece of vertical information I have to remember? Go on. VI is 0. If I forget that, I have not enough givens to proceed, okay, on this. So we have to remember that because we drove horizontally off the cliff, we were not moving vertically initially. Now that we have that, we can find the height of the cliff using D equals VI times T plus 1/2 AT squared. This is 0, so it won't matter. All I have to do is go 1/2 times 9.81 times 1.25 squared, and I have the height of the cliff. Oops, I forgot the square. All right, so the cliff is 7.6 meters high, I guess. Okay, everyone all right with that? It's not a very tall cliff. but you went off it pretty fast. Okay, questions on that one? All right, guys, that's what there is in Unit 1. All right. I mean, if you can do if you can do your graphing problems, you can do a projectile motion problem, an acceleration problem. Okay, that's what's going to be tested on the final exam, at least in the written response. Obviously, there will be some multiple choice questions that will involve some graphing. They'll involve the nature of acceleration, the nature of vectors, okay, and scalars and things like that. You know, simple things like if somebody walks down the hallway 10 meters north and then turns around and walks 5 meters south, what's their displacement? Like easy things like that, okay? But just the nature of scalars and vectors and that kind of thing. All right, so just make sure you go over some of the problems from the worksheet package from Kinematics, okay, to make sure you can still do those. You don't obviously have to do them all over again, but do a few just to see where you're at. I also posted on Google Classroom this morning the final exam review package. It isn't very big. All right, it's got 4 or 5 questions for each unit, because I'm only going to ask probably 3, maybe 4 questions per unit, okay, on the final exam. So, and in fact, it's probably less than that because some questions actually combine stuff from more than one unit in order to make the test a bit shorter, okay. So just know that that's kind of the way it's going to be set up. The test generally goes in order, okay, but not entirely. Right? It generally progresses through the units, but like I say, there are some questions that overlap units, and so you got to remember that. Okay, questions from you guys? Anything you want me to go over in more detail or talk more about or demonstrate from this unit?
Can the two types of projectile motion be combined?
No, they won't be combined. They're one or the other. So there's one projectile motion question on there. It's one or the other of those 2 types.
Well, we've done one combined, right? Like it's the angle on the top of the loop.
Oh, no, you won't have one like that. No, no, not at all. Yeah, because, I mean, why ask that? Like, guys, and here's the thing you need to understand, guys, about the final exam, because Ed just asked me, we did do one where these 2 types were combined when we had that thing at the top of the building, and so, like, it went up, and then it came back down off the building, and then there was this other part. You're not going to get one like that on the final exam, okay? My philosophy on final exams is this. They're difficult because of how much material is on them, not because of the difficulty of the questions. Okay, for me, I'm going to ask questions that are of moderate to maybe lower than moderate level difficulty, because I want to know, can you still do the stuff I taught you? Not, can I think up the hardest question I ever have and throw it on there and see if you can do it when you have to do a whole course worth of stuff. Okay, not everybody agrees with me. I like to think of them as wrong. Okay, but okay, not everyone agrees with me that I think that's what a final exam is about. It's difficult because there's a lot of stuff on it, not because I'm asking the hardest questions I've ever asked. Okay, what part specifically? Okay, so analysis means like doing the v equals or the y equals mx plus b. Okay, or okay, it could mean I give you let's say like it's a velocity versus time graph. Okay, and I ask you to calculate, what's the acceleration between here and here, right? And that would just be a VF minus VI over T kind of question. I could ask you, what's the total displacement over the whole trip? Okay, that's where you do the, right, the different shapes and, okay, because we're taking average velocity and multiplying by time when we calculate those shapes, okay, okay, how we use a velocity versus time, but that line's supposed to be flat. It's not supposed to be flat. Okay. Yeah, so just things like that. Nothing, like they say, that nothing I didn't already ask you, right? So what I've asked you before and what I've asked you on those worksheets is exactly the same kind of thing I'm going to ask there. So I might ask, yeah, calculate the displacement from velocity versus time graph, or I could give you, let's say, a position versus time graph. Let's say that looked like that, right? And I might ask you to describe what's happening. Okay, so in the first part, what's the object doing if this is a position versus time graph? Moving forward at a constant velocity, right? That would be the most correct answer, okay? If I had a position versus time graph that looked like this, the object would be accelerating. So that's what I mean by interpretation versus analysis. The analysis would involve more calculating. The interpretation would involve, I recognize what these shapes mean on a graph. Yeah. Okay, what else? Okay, well, like I say, I posted the review package. You might want to have a look over it. Okay, there's one sheet that's basically, here's the key points from each unit, okay, for the final exam. And then, like I say, there's another page that is, here's some old exam questions for unit 1. Here's some old exam questions from unit 2. Here's some old exam questions from unit 3, okay? And you can give them a try and see how you do on them, okay? But I would say right now, you should be looking at all kinematic stuff, and hopefully some more questions will come up. Okay, because guys, like, I want this review to be tailored to you. You've got to ask me the stuff you need to know. I've told you what's going to be on there, okay, in terms of the kinematics concepts and the types of questions I'm going to ask. Beyond that, there's not much more for me to say, okay, except that I want to tailor this toward what you need. Okay, so if you have questions you want me to go over, or you have something you want me to demonstrate or review, then I'm happy to do that. But it needs to come from you guys. Okay. So I'll let you have a few more minutes or a little bit of time here to kind of look at that stuff, and then maybe that'll trigger some other questions that we need to go over.